Okay, so today we're doing exponential and logarithmic equations. I love solving things, and hopefully you all do too. So we're going to solve exponential equations and solve logarithmic equations. So we're going to start here with the word problem. We have the population P of Arizona has been increasing at an annual rate of 2.3%. In 2010, the population of Arizona was 6.4 million. Write a formula for P of X where X is the year and P is the million. So writing the formula is pretty straightforward, right? So if I'm going to write the formula, grab my pen. So the formula here is our population X equals, and it's growing at a rate of 2.3%. Because that's growing, that means it's my whole population plus, okay? And its initial is 6.4. Remember when you're working with exponents, with exponential, we have f of x equals a times b to the x. A is our initial, b is what our changes. So, and x is our time, our beginning. So we have here 6.4 million. So that's our initial. We're growing at a rate of 2.3%. Because we're increasing, that means we're adding on to our 100% that we have. So my B equals 100% plus 2.3%, which equals 1.023. That's what my B is. So this is 1.023, okay? And then X is the years in million. Well, I'm starting at 2010. So X is the years, but minus 2010. I said X is the years in million. No, X is the years and P is in millions. So this is my formula that I'm following. Okay. Now it wants us to estimate the population of Arizona in 2005. So I want to be able to estimate that population. And I didn't mean 2005. I wrote 2014. That's a typo. I don't know why I wrote 2005. Estimate the population of 2014. So we have P 2014 equals 6.4 times 1.023 to the 2014 minus 2010. So I'm going to put this into the calculator. So let me grab my calculator. And I have 6.4 parentheses 1.023 to the, and I'm just going to write 4 because 2014 minus 10 is 4. And it's approximately 7 million. So in 2014, it will be approximately 7 million. Okay? How do we feel about reading and setting up and going from there? No questions, no comments, no concerns? All right, I'm going to keep going then. Let's type in there. All right, when light passes through water, sorry, keep clicking. When light passes through water, intensity I decreases according to the formula I of x equals I sub 0 e to the negative kx, where I sub 0 is the initial intensity of the light and x is the depth in feet. If determined symbolically and graphically, the depth x at which the intensity is 1% and I sub 0 is 500. Okay, so symbolically just means to solve it by hand or set up as much as you can by hand. And then graphically obviously means to graph it, right? So we are going to take our variables that we're given. So we know that 1% is going to have to become 0.01, right? And yeah, So let's plug everything in. So we have I of x, that looks like a 1, equals, and because this is the initial at this percentage, you're actually multiplying that. So this is 0.01 times 500. Okay, because it says it's 1% of that. Okay, and then that gives us 5. So we're starting off with a 5. Now we're going to write our whole equation. So we have I of x equals, and our initial is 500, I sub 0, or I naught, whatever you want to call it, e, and it's to the negative kx. And now we're going to need to solve our k. What is our k? I feel like I'm missing information from the problem. What am I doing wrong? There's a whole sentence missing. What happened to my notes, y'all? Let me get the whole problem. Pause. Here is the full problem. I was really lost on where we were going with that. So first off, we're going to read it again. When light passes through water, its intensity I decreases according to the formula I of x equals I sub 0 e to the negative kx, where I sub 0 is the initial intensity of light and x is the depth in feet. If I of x equals 500 e to the negative 2/10 x, determine symbolically and graphically the depth of x at which the intensity I is 1% of I sub 0. I really am confused on how this problem did not save or I don't know. Okay, so we're looking for I of x first. So we're going to find what that value. And so our I of x is going to equal 1% of our I sub 0. So 1% of our initial is going to be 5. 1% of this is 5. Okay, so we are taking 5. So we know what I of x is. It is 5. So we have 5 equals 500 e to the negative 2/10 x. And our goal is to solve this symbolically. So going through our PEMDAS, using our inverse operations, all of that is what we're doing. So instead of multiplying by 500, I'm going to divide by 500. When I divide by 500, I'm left with 5 100ths. No, 5 1 100ths. So 1 100ths equals e to the negative 2/10 x. Okay. Previously, we talked about the inverse of e is natural log. So the inverse of e is natural log. So I'm going to take the natural log of each side. So natural log of both sides. So I have natural log of 1/100 equals, and this is going to set the exponent free. And that's because e to the natural log, they're inverses of each other. And we get negative 2/10 x. And then my last and final step is to divide by negative 2/10. Okay, so I can put this in the calculator and get an approximate value of my x. So going to my calculator, I'm going to type in natural log of 100 divided by negative 2/10. And I get approximately 23 300. Okay, so 23 300, that represents the depth. So this is feet deep. I want to specify. So in order, what happens is to be 1% of the initial intensity, I would have to be 23 feet deep into the water. Okay. Now, graphically, if you're doing this graphically, you are inputting into y equals. Your y1 is your left side. So my left side was just 5, right? Your y2 is your right side, and my right side is 500 e to the negative 2. Let's see, so I need to take attendance. Negative 2x, and then I hit graph. And it's thinking, and it's like, oh, I can't see anything, so I'm going to go to zoom, and I'm going to try zoom fit, see if it'll find it for me. Let the calculator do some work. Sometimes zoom fit goes way too far in. So it's all right. I'm going to zoom out a little bit. Move my little spider. I call him my spider, because I can make inference that it's somewhere over there. And somewhere in here, these two intersect. And so even though I can't see it perfectly, I can hit second trace, and I'm looking for the intersection. And it's going to find the first curve, the second curve, and it's like, you want us to guess for you? I'm like, yeah. And what do I get? Oh, 23 and approximately 300. Okay, so that's it graphically. You can change the window, the settings of the window to get a better view, a better intersection. That's the gist of it. Any questions about one, making sure the whole problem is present, but solving it by hand or graphically? None? All right, let me make sure this whole problem's here. The concentration of the drug in a patient's bloodstream is modified formula. And so these measures are milligrams. What is the concentration? Yes, the problem here is that t should be an exponent, and I don't know why it's not. T is an exponent. So it's a little t. Crazy, crazy, crazy. Things are doing weird things. All right, so what is the initial concentration of the drug? So we're looking for the initial concentration. So if you're looking for your initial, that's your C0, right? That's when x equals 0. So I have 11 times 72 hundredths to the t. When I when I plug in 0, that's going to give me 11 72 hundredths to the 0 power. And anything to the 0 power is 1. So this leaves me with 11 times 1, which equals 11. So my initial is 11 milligrams per liter. Okay, so that's my initial. Also, remembering what this coefficient means is helpful in identifying your initial. But if you forget, that just means you're plugging in 0 for your independent variable and solving for the dependent. Okay, now it's asking us, how long does it take for the concentration to decrease to 50% of the initial level? So I am looking for C of, not X, but C of T. So I have C of T equals, and I want it to be 50% in the initial. So 50% of 11. So I needed C of T to equal 5.5. All right, so that means I have 5.5 equals 11 times 72 hundredths to the t. And I'm going to go through the process to get it by itself. So the first thing I'm going to do is divide by 11, right? Divide by 11, divide by 11. And this is just 5/10. Okay, so I divided by 11. And remember we talked about you could take the natural log, you can take the common log, you just have to take the log of both sides, whether it's natural or common. So we're going to just take the natural log of both sides. It's less characters. So natural log is one less, I know. The natural log of both sides. What the natural log does on the right-hand side is it sets my variable free. So t natural log of 72 hundredths. And now I can get t by itself. So I divide by natural log of 72, divide by natural log of 0.72. I'm going to put that in the calculator. So I'm going to go to my calculator. And so I have natural log of 5/10 divided by natural log of 72 hundredths. And that gives me approximately 2 and 11 hundredths. So t is approximately 2 and 11 hundredths, and that represents the time. So, and our time is in hours. So about 2 and 11 hundredths of an hours. Okay, I think I have this pretty written, yeah. So kind of going over what we did, initial concentration, found it. 50% of 11 gave us our milligrams per liter that we were trying to solve for. We divided by 11. We took the natural log of both sides. We divided by the natural log of 72 hundredths, and we got our value. Okay. Next. So in 1945, computers could perform about 1,000 computations with 1 kilowatt hour of electricity. We're going to use the formula E of x equals 1,000 to the 5/8 power x to determine when 1 billion computations could first be performed with 1 kilowatt hour. So we're looking for that 1 billion, right? 1 billion equals this. So the first thing that we're going to need to do is divide by 1,000. So we divide by 1,000, and then after we divide by 1,000, we take the natural log of both sides. So when we take the natural log of both sides, it sets our x free, and that allows us to now divide by the natural log of 2 to the 5/8 power. We divide, put it in the calculator, and approximately 32. And so, 32. So we are going to then add, so we need, there we go. Since x represents the number of years since 1945, the years it would take all the way up to 1977. For it to perform 1 kilowatt of hour. And that would be it. So again, your goal is to simplify by dividing, then isolate your power by taking the natural log or common log, whichever your heart tells you to do. And then once your power is free, then you divide, type in the calculator, get your value. All right, now, by hand. So here we have pretty straightforward problems, not word problems, just solving, and there we go. All right, so 9 to the 2x equals 9 to the 4 minus x. As long as the bases are the same, all you're doing is focus on the powers. As long as the bases are the same, all you're doing is focusing on the power. So my powers are 2x and 4 minus x, okay? So once this is just now an Algebra 1 problem. And my goal is to isolate x by combining like terms and using inverse operations. So I combine my like terms. The opposite of multiplying by 3 is to divide by 3, and bam, x equals 4/3. Okay, next, let's do another example. So this one, we have a little more to do. So on here, we have 6 times 1.3 to the x minus 4 equals 20. What we want to do first is get our power and its coefficient by itself. So we're going to subtract 4 from both sides. When I subtract 4 from both sides, I'm going to be left with, add 4 to both sides. I subtract, my bad. Add 4 to both sides, and this is where we are. Now we want to get the base and power by itself. So I'm going to have to, instead of multiplying by 6, I'm going to divide by 6. So I divide both sides by 6, and we get, and now it comes down to taking the log of both sides. Again, you can take the natural log or the common log of both sides. So when I take the natural log of both sides, it's going to set my x free, allows it to be a coefficient, a factor. And now I can divide. So I'm going to divide by natural log of 1 3/10 on both sides, type it in the calculator, and I get my approximate value. How do we feel so far? No questions, no comments? Okay, we're gonna keep going. If you need me, well, I tried to save time because this is a lot in this section by having it, a lot of it pre-typed. But if you need additional questions, comments, or anything, let me know. But here we go. So we have 1/2 1 to the 1 minus x. And notice here, I cannot just focus on the powers because the bases aren't the same. So I'm going to go ahead and take the log of both sides. I chose to do this problem showing that you can do it with common log as well as natural log. Uh-oh, I went too fast. So I'm going to take the log of both sides. So when I take the log of both sides, that sets my power free and turns it into a factor. And so now I have 1 minus x log of 1/2 equals log of 1/7. Okay, I need to work on getting x by itself. So the first thing I need to do is divide by my log. So the first thing I'm doing is dividing by log 1/2. So I divide both sides by log 1/2. And x is not quite by itself. And so I need to get x by itself, which means I'm going to subtract 1 and multiply by -1. Makes sense? Or multiply by -1 and then add 1. It's subtract, add 1. It's really up to you, but it's going to leave me here. So we have x equals 1 minus log of 1/7 divided by log of 1/2. That is the exact answer, right? To get my approximate answer, I put it in the calculator, and I'm going to get approximately -1 and 800,000. Okay. No questions, no hesitations. I don't see anything popping off in the chat window, so I think we're okay. If we're not okay, let me know. All right. Now, what happens when you're dealing with E? Well, it kind of makes the problem easier. Things are going to eliminate. Yep. So here we go. We have 4 to the 3x equals e to the x minus 2. I'm going to take the natural log of both sides. So when I take the natural log of both sides, I'm going to be left with natural log 3x natural log of 4 equals x minus 2. And then my goal is to get my x's together. So I need all x's on one side and all non-x's on another side. So I'm going to actually subtract x. And when I subtract x, that allows me to factor out x. So when I factor out x, I'm going to be left with 3 natural log 4 minus 1 equals negative 2. And now all I have to do to get x by itself is divide by 3 natural log of 4 minus 1 equals negative 2. That is my exact answer. To get my approximate, I'm going to plug it into the calculator. And I get my approximate. Okay. Now this we're going to do it without having to take the natural log of both sides, because the base on the left can be changed to look like the base on the right. Well, they can both be changed to look like each other, and that's because they're both multiples of 3. So 9 is 3 times 3, which makes it 3 squared. And 27 is 3 times 3 times 3, which makes it 3 cubed. And we're going to use our power rule. And so our power rule says that I'm going to multiply 2 times x plus 5 and 3 times 3x. And now my bases are the same. And so all I have to do is focus on my powers. So that's setting 2x plus 10 equal to 9x. And now it's back to being a algebra problem, algebra 1 problem, pre-algebra problem at that. I'm going to combine like terms. And then I'm going to use inverse operations to get x by itself. So 10/7 equals x. And then I can put it in the calculator and find the approximate, but I stopped right there. So I tried to go through the various types of problems that you'll see and be working with. Are there still no questions? Okay. All right, so a pot of coffee with temperature 90 degrees Celsius is set down in a room with a temperature of 25 degrees Celsius. The coffee cools to 60 degrees after 1 hour. Find the values of T sub 0, D in A, so that T of T equals T sub 0 plus D A to the T. Okay? So the room has a temperature. That's your initial, right? Makes sense? So my initial is the room temperature. So my T sub 0 is 25 degrees Celsius. And the initial temperature difference between the coffee and the room is the D. So the initial temperature difference here would be my coffee is 90, the room is 25, so D would equal 65. So that gives me T of T equals 25 plus 65A to the T. Next, we have to solve for A. So to find my A, I'm going to use the initial point that was given to me. And the initial thing that was given to me was that after 1 hour, the coffee has cooled to 60. So I'm going to use 1 as my T and 60 is my T of T. So I plug that in. And then I do the math. So I'm going to subtract 25, divide by 65. When I subtract 25, I get 35. When I divide by 65, I get 7/13. So my equation is T of t equals 25 plus 65, 7/13 to the t. And now, since I have an equation, I can answer any question that comes in regards to this problem. So the question that we're going to answer is just find the temperature of the coffee after half an hour. So now it's telling me what my T is. So T equals 1/2 because that's half an hour. So I'm going to plug in what I know. I plug in for 1/2. I know that my A was 7/13. And I'm going to type this in the calculator just as I see it. And the calculator is going to tell me 72.7 degrees Celsius. Okay. And now, how long does it take for the coffee to reach 50 degrees Celsius? So we're trying to figure out how long is it going to take for the coffee to reach 50 degrees Celsius. Well, this time we are solving for T. So T of t equals 50. So 50 is going to equal 25 plus 65, 7/13 to the t. And we're going to solve. So we subtract 25. Then we're going to divide by 65. Okay. And then we simplify. And now we're going to take the natural log of both sides. Or the common log. I'm sorry, I didn't know what I did. Forgot what I did. And so once I take the common log of both sides, I'm now able to get t by itself. So t exactly is log of 5/13 divided by log of 7/13. Well, you don't tell time that way. So then I'm going to use the calculator to approximate. And so t is approximately 1 54/100. How long it takes. So almost 1.5 hours. So that's an hour, 1 hour and 32 minutes. And so how did I find the 32 minutes? I took 54/100 and times it by 60 to get my 32 minutes. And we have 5 minutes left. Do I think I can go through this one? Yeah, I can do this one. This will be our stopping point. All right, so solving this graphically to the nearest thousands literally is in the calculator. So in the calculator, you're going to put in the y1 as your right side, your left side of your equation, your y2 as your right side, and again, you're finding where do they intersect. And notice how they intersect at 2 places. So you're going to have to find the intersection more than one. So you'll find the intersection to the left and get a value, and it tells you what it is. And then you're going to have to find the intersection to the right and get a value, and it'll tell you what it is. It's pretty straightforward in the calculator. And that is where we're going to stop today.